So now we're moving on to covalent. So with ionic bonding, you just had the giant ionic lattice. With covalent bonding, you have a number of different substances that you need to know about. When non-metal atoms react together, they need to gain electrons to fill their outer shell and become stable. Incomplete outer shells. They can only do this if they share electrons with each other. Both atoms have a full outer shell. Okay, so each hydrogen will share an electron with the other, and now they've got 2 electrons that can help both of them out. A shared pair of electrons is called a covalent bond, and covalent bond only happens in non-metals. Okay, so we're sharing shared pairs of electrons. Many elements exist as molecules, 2 or more atoms joined by a covalent bond. Each atom has a full electron shell and is therefore stable. Hydrogen, oxygen and chlorine are like that, as are nitrogen and all of group 7. Only the outer shell of electrons is involved in covalent bonding. This means that the inner shells do not always have to be included in diagrams. 2 different ways of representing a covalent bond. We have the displayed formula, which is just a black line, or we have a dot and cross diagram. Either of those is acceptable for covalent bonding. So pause for a minute and see if you can name these and write their molecular formula, which tells you what atoms are present and in what ratios. Pause for a minute, jot them down and restart when ready. First one, methane CH4. Second one, ammonia NH3. Third one, oxygen O2. Fourth one, water H2O. Fifth one, chlorine Cl2. Okay. The number of covalent bonds formed by an element is called the valency of the element. Okay, so in group 4 we have carbon and silicon. They have 4 outer electrons and form 4 bonds, so their valency is 4. If we look at nitrogen and phosphorus, they have 5 outer electrons. So to make it up to 8, they form 3 bonds and their valency is 3. Oxygen and sulfur are in group 6 with 6 outer electrons, therefore they form 2 bonds and their valency is 2. And fluorine and chlorine are in group 7. They form 1 covalent bond, their valency is 1. Drawing a dot and cross diagram. We use dots for electrons that have come from one atom and crosses for electrons from the other. Okay, what about a water molecule, H2O? Hydrogen needs to gain 1 electron, oxygen needs to gain 2, so oxygen bonds with 2 hydrogen atoms to make a molecule of water. Okay. How can we show covalent bonds? Well, methane is a hydrocarbon. This means it's made of only hydrogen and carbon. Methane has the chemical formula CH4. Each carbon needs to gain 4 electrons and each hydrogen needs to gain 1. There are several different ways we can show this. There's the 3D ball and stick model, the 2D ball and stick model, the dot and cross diagram showing outer shells as circles, and the dot and cross diagram showing outer shell electrons, and the displayed formula showing bonds. And you might have to pick out the advantages and disadvantages of various models. So you might talk about the ball and stick models. They're good because they show you the ratio of atoms clearly, but they don't show you the bonding electrons. And you might say that the dot and cross diagram shows you the bonding electrons, but doesn't show you the angles of the bonds in the model. So looking at models and finding out their limitations, finding out their advantages and their disadvantages. So this particular slide shows you the main advantages and main disadvantages of each of the ways of representing methane. Have a look at them and see what you think would be the easiest advantages and the easiest disadvantages to remember, and you should be able to apply those to any exam question that you might get. Remember folks that you can either represent a molecule of a covalent substance by a dot and cross diagram or using black lines. So hydrogen here has one shared pair, a single bond. You would draw one black line between two hydrogens to represent that. Oxygen, you can see, has two shared pairs in the overlap. You would represent that as two black lines if you were drawing out oxygen in the displayed formula. Nitrogen has three shared pairs of electrons in the overlap. You would draw that out as a triple bond, three black lines. If you look at these covalent bonding diagrams, these are ones that you'd need to know for your exam. We have oxygen here with one double bond, two shared pairs of electrons. We have ammonia here, three single bonds, okay, between the nitrogens and the hydrogens. Nitrogen with one triple bond, three shared pairs of electrons. Water with two single shared pair bonds. And carbon dioxide with two double shared pair bonds, and last but not least, methane with 4 times single bonds. Okay. Now, we are going to be looking at some giant covalent structures, and there are a number of substances that form giant covalent substances, but we have simple molecules to look at first. And simple molecules have strong covalent bonds between atoms, but weak forces between molecules that are called intermolecular forces. So here you can see weak intermolecular forces, but strong covalent bonds. Please try to remember that. That becomes important. So simple molecular covalent compounds, they have strong covalent bonds between atoms, but weak forces between molecules, giving them low melting points and boiling points, and meaning that their state of matter at room temperature is often liquid or gas. So, if we wanted to describe their structure, we'd say they were covalent, we would say they were simple molecular, small molecules, shown by lines in the diagram, liquid or gas at room temperature because they've got a low boiling point, and a low boiling point because their intermolecular forces are easily overcome by heat. Okay, ladies and gentlemen. So, simple molecular substances. Molecules we've looked at so far are called simple covalent molecules. Strong covalent bonds, weak intermolecular forces between the molecules. So simple molecular substances have low melting and boiling points, so they're often liquids or gases at room temperature. They do not conduct electricity as a solid, liquid or a solid or a liquid, or when dissolved in water. Why do they have these properties? Well, they have low melting and boiling points because they have weak intermolecular forces that are easily overcome by heat, and they do not conduct electricity as a solid, liquid, or when dissolved in water because they got no free electrons and they've got no free ions. So this is a giant covalent structure, and you would look at this in an exam and see that it's made of carbon. And if you look at a atom in the middle of the diagram, you would see it's got 4 bonds coming out of it. Therefore, we're talking diamond. You know clearly that diamond has a very high melting point. Your explanation for that would be that much energy is needed to break the many covalent bonds. You can see that here the carbons all have 4 covalent bonds. So because they've got 4 covalent bonds, they don't conduct electricity because they've got no free electrons. Okay, no free ions or electrons. Okay, 4 bonds per carbon. Click through those again. You can see that there are interlocking hexagons here for graphite, and you've got layers of interlocking hexagons. If you take one layer off the top of graphite, so you've literally got one layer of interlocking hexagons, we've got a giant covalent structure. It's not graphite anymore though, it's graphene. Still got a high melting point, still much energy needed to break the many covalent bonds. Does it conduct electricity? Yes. Why? Because there's 1 free electron per atom free to move and carry charge. Lots and lots of different covalently bonded substances. If you see a ball like this, it's C60, you can see it's a ball of hexagons and pentagons. Okay, type of structure, it's a molecule. We're going to call it Buckminster fullerene. Its melting point is going to be high because much energy is needed to break the many covalent bonds. And you can see that there are only 3 bonds per carbon, not 4. So therefore, yes, it will conduct electricity because there's 1 free electron per atom free to move and carry charge. So, for structures and bonding, you touch very briefly on polymerization. Polymerization is a process that is covered in more detail in separate science. But for combined science, you touch very briefly on the fact that polymerization will make polymers. We know polymers as plastics. Okay. So, if you wanted to know, if you want to name the types of reactant that you'd use in polymerization, it's called a monomer, a single unit. So the reactant below there, you see C double bond C surrounded by 4 H's. That is ethene. And if you can get lots of ethenes together and you can get their double bonds to break and then to join up in a long chain, that long chain is then called polyethene. Okay, so you've got monomer ethene joining up to make polymer polyethene. So you're making a polymer polyethene. And because you can see black lines in this diagram, the type of bonding is covalent. Okay, ladies and gentlemen. Metallic bonding, our last type. in metallic bonding, you have got free electrons, a sea of free delocalized electrons in layers of metal ions. I know it says free electrons from outer shells of metal atoms, but by losing those outer electrons, you have the formation of metal ions and layers of metal ions. Metal atoms lose their outer electrons to form ions. The ions are arranged in a regular lattice, one on top of the other. Delocalized electrons can move all through the crystal. The electrostatic attraction between the positive ions and the electrons hold the structure together. Properties of metals: high melting and boiling points, good conductors of heat and electricity, and they're malleable because they can be bent and shaped. The reason they have high melting and boiling points is because there's a strong electrostatic attraction between the electrons and the ions. The reason why they're good conductors of heat and electricity is that they have delocalized electrons that are free to move through the metal. Okay? And they are malleable. Layers of ions can slide over each other and delocalized electrons still hold the ions together. That's why they can be bent and shaped and hammered. So if you see a diagram like this, your type of bonding is metallic. What happens to electrons? They are delocalized or free. What is the type of structure? Giant metallic structure, and any metal, copper, gold, silver, you name it, any metal. We know melting point is high. Why is melting point high? Because much energy is needed to break the electrostatic attraction between ions and electrons. Do metals conduct electricity? Well, yes, they do, don't they? Why? Because they have free delocalized electrons that are free to move and carry charge.